As we've just mentioned, wear leveling is a flash controller feature that makes sure you don't end up with a horrendously uneven balance of write workload across your pool of flash cells. An uneven balance will result in hotspots, with cells in these hotspots dying off before the rest of your cells, and we definitely don't want this. So let's look at some pictures to help explain the process of inline wear leveling. The end result being a flash device where each and every cell is used to the same extent. Here we've got a picture of a flash device on the left with 12 flash cells. Obviously it's a horrendously oversimplified example, but this doesn't matter, it's good for illustration purposes. This device obviously is not employing wear leveling, and consequently some cells have been hit far more than others. In our diagram we show this as a heat map. The red cells have been programmed and erased a lot more and are nearing their manufacturer specified end of life threshold. They will wear out really soon, whereas the green and yellow cells have been hit a lot less, and these could be considered underutilized. On the right we show the same 12 cell flash drive and how it could look if it employed wear leveling. First of all, we show how this same device would look if the worst case was so. And finally, we show how it could look if the best case was so. The point being that both of these options on the right are highly preferred over the option on the left. Now let's take a quick look at how inline wear leveling works. In this example, we've got an incoming write. The write is for LBA 914, which the controller has mapped to cell 0, the top left cell. But as the controller knows that this cell is nearing the end of its usable life, it remaps the write I/O to one of the less used cells. And it'll continue to do this until all of the cells in the device become evenly used. It's pretty simple. Okay, back to our original slide. Last but not least, flash over provisioning. This is another trick that flash devices use to improve both performance and device lifespan. The concept is fairly simple. Hide some of the physical capacity of the device and reserve this hidden capacity for the controller to use in order to increase performance and reliability. An example of how hidden capacity can improve write performance is like this. If we think of a busy flash device that is nearly fully utilized from a capacity perspective, writes are coming in thick and fast. In fact, so fast that the controller is unable to pre-erase blocks in the background. This means that we're suffering from write amplification. In other words, we're going through the process of writing zeros back to ones, which we explained earlier can be a real overhead for a flash device. And we're doing this because we don't have pre-erased or fresh out of the box flash blocks to write to. Now then, let's say that the flash controller had a handy little stash of, let's say 50 gig of flash memory that it wasn't telling anybody about, and this is still in the fresh out of box, pre-erased, purged state. The controller could then easily use this 50 gig of free space to start performing faster writes. Pretty simple really, and it's important to note a few things here though. All decent flash devices do this, and at no point does the usable capacity of the flash device increase. As far as the higher levels in the stack, operating system, hypervisor, all of those guys, as far as they're all concerned, the capacity of the device never changes. This space is hidden, and it's only ever used in the background by the controller. Now that we've discussed some of the techniques used to improve the performance and the lifespan of flash memory, let's take a look at what's being referred to as enterprise grade MLC, or eMLC for short.